am starting the recording now, and Tony has agreed to be my deputy, and so from time to time I'll be reaching out to Tony. Okay, so today we're starting with, as we often do, with a unquiz. And so here it is. And I will give you 10 minutes to do it, and then we'll go through it. So everybody, please start working on this.
We can't see anything.
Oh, well, thank you. That helps. Thank you, Tony. So I need to do something to fix that. That's probably easily done. Okay, so I have to hit about a half a dozen buttons here. Now, can you see something, Tony?
Yep, we can see it.
Great, thank you. Okay, so now we're, so I guess we'll let the clock start now. It'll be about 10 minutes. Okay, Tony, you can hear me still, yes?
Yep.
Okay, excellent, thank you. Okay, so what we're going to do is we're going to go over this. Now, again, the unquizzes, I think, are an important part of what we're doing because it gives you an opportunity to have all the benefits of a quiz without any of the trauma or anxiety with it. Some of the benefits are you can see, oh, that's the kind of question that Jim might ask on a high stakes assessment. It also allows you to assess, gee, could you do this? Now, even though I will let you use, when I said unquiz rules, I let you use your book or your notes if you want to. But you really, other than that, you should be using, doing this by hand because that's what you're going to be doing on the high stakes assessment, without the use of calculators and actually without the use of notes on the high stakes assessment. And it allows you to assess, oh, are you understanding? Are you caught up? Now, it doesn't mean you're a bad person if you're not caught up, but we're approaching a weekend, so that is it. But you are grading this yourself. You are getting credit for doing these, but you sort of grade it yourself, so it's kind of a self-assessment kind of thing. Okay, so let's dive in and talk about the solution. If you got the answer, congratulations. If not, you'll learn something, and so let's go into it. Okay, so I ask you to determine the volume of the solid obtained by rotating the region bounded by this parabola, y equal x squared minus 6 x plus 9, and y equal minus x squared plus 6x plus 1, about the line x equal 8. So let's go into it. And as usual, what happens is the first part on these problems has to deal with sketching a picture and drawing a slice. So let's spend a little time talking about this. Now, the function that was y equal minus x squared plus 6x minus 3, you know from your pre-calc that this is a parabola that opens downward. And you know from calc 1, the vertex, the maximum value happens whenever this derivative, which would be minus 2x plus 6 is equal to 0. So the vertex of this thing is going to happen at 3. So you know it opens down and the vertex is at 3. So you have an idea of what it looks like. Now this one, y equal x squared minus 6x plus 9, you know it opens upwards from pre-calc, and you also know that the vertex of this is when 2x minus 6 is equal to 0, which is also at 3. So you can sketch these and you can say, oh, these things are going to intersect in 2 points. You don't necessarily know what the points are yet, but we'll work through that. But the other thing that you know straight away after you start sketching this picture is that I'm asking you to take it around the vertical axis, x equal 8, which is this dotted business that you see on the right-hand side of your screen. So you see you're taking this green area and you're kind of going whoop, 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 whoop around this axis. Now we have learned 2 ways to do this. We can do perpendicular slices to the axis of rotation like this, or we can do parallel slices, and that leads to different formulas and everything else. But often one is better than the other. In fact, let's talk about, and we're going to choose not to do this, but you see we'd have a bit of a problem if we were doing slices this way, perpendicular to that dotted line, because that would mean we're integrating dy, and that would mean we would have to solve this quadratic for a function of y, and we have to solve this quadratic for a function of y. Now that's possible, but it's not trivial, and so that's kind of enough for you to maybe say, wow, that's going to not be an easy way to go. But if you consider the vertical slices like this, that means we're doing dx. So I already have this as a function of x, and this is a function of x. And so, we're saying, oh, the shell method is probably better, and we're going to be doing dx for this problem. Now, if we're doing dx for this problem, we still don't know what these points are yet. We just knew that this was one that opened down and this was one that opened up, but it's easy to find those. So let's move then to doing that calculation. And so what we're going to do is we're going to set the 2 equations equal to one another, and we'll solve it. So we'll say x squared minus 6x plus 9 is equal to negative x squared plus 6x minus 1. Now, to solve this, and you could see sort of from the geometry, there's going to be 2 points of intersection. We're trying to find the x, but to solve this, you get everything on one side, and you end up with 2x squared minus 12x plus 10 is equal to 0, and you factor it. And you conclude that x is equal to 1 and x is equal to 5. Now, to find out what the other coordinates are, you're going to take 1 and you'll substitute 1 into actually either one of these equations, and you would get 4. And to get with 5, you'd substitute 5 into either one of these equations, and you would get that y is 4. So you end up with, you know, the picture that we have. And I think I've talked about all the information that we need and that we have. So we're going to be drawing then, based on my discussion, we're going to be drawing vertical slices, and we're going to be doing the shell method. Okay, now here is a picture of this, and the picture is useful. Now here is the axis of rotation, and so see, when you're taking that slice, that rectangle, rotating around, you're getting something that looks like this. So now we can, you know, start talking about this. Is going to be 2 pi, the integral of the radius times the height of these cylinders. So we're going to say, well, what does this representative thing look like? Okay, well, I'm going to go back to this picture of it. You see, what you're doing is you're taking this green thing and you're going around here. So the radius is, and let's just pretend I drew the slice here. So the radius goes from here out to there. Now, if I had gone from here, the dotted point, all the way to the y-axis, it would be 8. But I stopped short of that. And in fact, the slice is happening. In fact, let's go back to the other one now. Okay, the slice is happening at x. And so what happens is you're not going 8, but you're going almost all the way. You're stopping short by that, so it is 8 minus x. So that is the radius of this thing. And again, the radius is going to be different depending on what x is. Right here, the radius would be a small number. Over here, the radius would be a bigger number. So, you know, it is, like we said, it is 8 minus x. So that is the radius. And the height, though, is pretty easy to figure out, I think. So the height is going to be the difference between these two, the top curve and the bottom curve. So what you're going to be doing is you're going to take the top curve minus the bottom curve for the height. And if you do that subtraction, you'll get minus 2x squared plus 12x minus 10. So we know the radius and we know the height. Okay, so we know the radius. And we know here they call it width, but down here they call it height. So I don't care what you call it, but it's going to be, it's this. Okay, so the representative slice, and again, it's very important that you draw the slice, I think, to do this, is going to be, because this is the formula we derive for the shell method, is going to be 2 pi radius, there it is, times the height. Now, there is algebra involved, so you have to multiply 8 minus x times this trinomial, and so this is pre-calculus calculation, but you got the 2 pi there, and when you multiply all this out and simplify it, because algebra is your friend, you see you're going to get some terms that have x squared in it. So for example, when you take 8 times minus 2x squared, you get a term with an x squared in it. And when you take x times 12x, you get a term with an x cubed in it. So you get something that looks like this. So what we have is 2 pi times, and algebra is your friend, you want to simplify that. So this is a of x. So that's what we're integrating. So the volume then, by the shell method, is the integral from 1 to 5. We figured out those were the values for x. The 2 pi is here. Now, the very first thing that I would do if I were calculating this integral, I would pull the 2 pi outside of the integral. So, you know, it would go outside here. Again, you don't have to do it that way, but that's what I would do. Let's talk about integrating this, though. This would be minus 80x to the 0. So I add 1 to the exponent, divide by the new exponent. I get minus 80x. I go here. The 106 just sits there. But here I add 1 to the exponent and divide by the new exponent. I get x squared over 2, and then I simplify. Here I add 1 to the exponent and divide by the new exponent, it's x cubed over 3. So I get this. And over here, I add 1 to the exponent, divide by the new exponent, and I get this. And then we plug in the numbers. Now, the pi is still there. So it doesn't go away, and it should be in your final answer because I'm asking you for an exact answer for this. Your top limit is pi, so you plug 5, you plug it into there. Again, you're not using calculators, so it's actually quite a bit of calculation here on this one. Minus, you plug in 1 to that. And at the end of this, you should get 640 over 3 times pi. Now, what I'm going to do is I am going to pause for a count of 10 Mississippi for questions. Now, what I'm really asking for is questions about this problem right now. After we finish with this unquiz, I will give you an opportunity to ask, more general or other questions. But I'm really asking for questions about this discussion that we just had. And again, I'll do a count for 10 Mississippi. Now, Tony also agreed to watch the chat, and so some students maybe don't have a microphone, or I don't know. But I will tell you that my preferred way of you asking a question is for you to go on mic and do it. If you cannot, and you want to pose a question on the chat, you can do that. And Tony agreed to alert me if there's a chat I should pay attention to. But I'm beginning my count now, and so I'm going to count to 10.
I had a question real quick.
Okay, excellent. Go ahead, please.
The one part I was confused about, and I'd like you to go over, is finding the radius as 8 minus x.
Okay, I will, talk about that again. Okay, and I'm going to start back here on this picture. Okay, now I'm assuming that the student says, okay, I'm good with why we would want to draw a vertical stripe, a vertical strip. Okay, so I'm drawing a strip here. But you see, I'm taking it around this axis over here, and I'm wiggling my cursor trying to make it look like I'm going around there. Okay, so what happens is I have to know how far is it from this point to where my strip is. Well, a good way to think about that is shown here. So let's suppose that that my strip is over here. Now the distance so it's a vertical strip. So the distance from the y-axis to this point is x, because we're integrating dx. We figured that out from our strip. So that part is x. But how far are you from the axis of rotation, which is x equal 8? Well, here is 8. So you see, if I went all the way to the y-axis, it would be 8. But I stopped short. And how much did I stop short? I stopped short by x. So this radius is 8 minus x. And I'm going to pause there just because I think that may have answered your question. Did it?
Yeah, it makes more sense looking at it.
Okay, excellent. Now, anytime a student asks a question, my plan is to start my count again. So I'm starting my count again.
When determining the volume, you plug the area into it, right?
Okay. I'm not sure, and again, I was listening to your question, but there was some noise on the line, so I'm not sure I understand your question, but I will try to address your question, and then I'll go back to you and see if I answered your question. And again, I'm speculating just a little bit about what your question is. Okay, so one thing that we learned from the last lecture is that the area of a cylinder is going to be given by 2 pi times the radius times the height. So that comes from the last lecture. That's the formula that we're going to use for the shell method. And the student who asked the question before was talking to me about what the radius was, and that's how we found out that the radius of the representative cross section was 8 minus x. Now, to address your question, and I'm trying to address your question. So 2 pi is 2 pi. We know we need to integrate this, but now we need to know what is the height of that representative rectangle. Well, the height of that rectangle, representative rectangle, is going to be the top function minus the bottom function, because it's the height of this strip right here. So it's going to be this one minus this one. So, and it's kind of shown here. So it's going to be this one minus this one. And so when I subtract those two, I get the height is minus 2x squared plus 12x minus 10. Okay, so what we're doing is we have this representative height and radius as a function of x, and then we do some algebra simplifying. So then the volume is found by the shell method integrating this, the formula 2 pi, and we talked about that. Now it's possible, because the technology wasn't perfect and your question didn't come to me very clearly, but I was trying to answer what I thought your question might have been. Are we good, or did you have a follow-on question?
It was about that you take the area and then plug it directly into the volume equation, right?
Yes, we did.
Okay.
And okay, so yes,
Thank you.
but and that's because the way we structured the problem, we had a uniform cross section, but it was cylindrical shells. So this is the shell method. Okay, I'm going to start my count again. Okay, I hit 10 Mississippi. So, and again, your questions are always welcome, but I think we're going to move on. And let me find the slide I want to talk about. Okay, so that was an unquiz. That was fine. All right, here's where I want to be then. And by the way, I'm going to do just a little bit of cockpit commentary with you. But after I finish the cockpit commentary, I'm going to go back and ask if there are questions. And this is about a general question, okay? So, I mean, a student could ask, oh, is there extra credit in this class? And the answer to that one is no. But I mean, these are general questions that I will ask for. But let me give some cockpit commentary. It is important for students to realize that we've reached the COD weekend. At the end of this class, we will not have class again till Monday. Now, that gives me an opportunity to do some math. It also gives you an opportunity to do some math if you need to catch up or something like that. So you know, work goes on and things like that, but the class doesn't until Monday. So everybody should be aware of that. I also think that we're on schedule, and by the end of this class, I expect that we will be exactly where we want to be with the material. So you know, just speaking from the cockpit, we're on course and we're on schedule, so that's a good thing. But I also would say keep your seatbelts buckled, because this is you know, what's going on. And also, I'm going to say that not only am I doing math this weekend, but Jesse Hayes Carver is doing math, and I know that some of you have gone to his guided study groups, and I'm pretty confident that those end up being really good things. And so anyway, that's pretty much the end of my cockpit commentary. And so now I'm going to go to you know, throwing out if there are any questions that anybody wants to ask right now. Now the questions you know, could be anything, and I'm going to do a count of 10 Mississippi just to capture any questions that are there. And I heard some kind of a noise. I don't know if that's somebody raising their hand, or somebody putting something in the chat box, or somebody leaving to, you know, tend to a barking dog or something. So I don't know what that noise is, but Tony is kind of watching that for me a little bit. But if you have a question, again, my preferred method is for you to go on mic and shout it out. And then we will try to do, with Tony's help, we will try to do the other things as well. So I'm starting my count now.
I have a question.
Yes, go ahead.
So I also sent you an email about this, about the LSA assignment. So it only has like a spot to turn it in Blackboard. So what is that actually?
I'm sorry, I'm going to have to ask you to repeat that and perhaps repeat it just a little bit more slowly because I do want to answer your question. So please go ahead again.
Okay, so in Blackboard there is like a LSA assignment, but there's nothing in
There is an LSA that has been assigned, yes.
So what should we actually do for the LSA?
Well, the LSA, okay, so to answer that question, I'm going to go and try to find the LSA. Now this is like, so I'm hunting for the LSA. You know, I went over it in the class and in the videos, and Jesse Hayes Carver probably will be, I guess maybe I have to go all the way back to Blackboard. So I'm thinking, so I'm wow. So I'm going to have to go, I guess I have to open another browser to do this. And okay, so I guess I'm just going to close this. Oh God, it's closing two tabs. You know, I don't want to close the tab where you guys are living. You guys are living in that browser, so I'm closing, I think I'm closing Firefox tabs. Okay, so I have to go here and I'm going to go to, and I'm doing Firefox now because I have to open a Firefox tab, and I'm going to go to Blackboard at COD. So I'm here at COD, and in a bit I'm going to do this. I don't know. Okay, so let's open this. All right, so I'm just going to say bb.cod.edu. I have to log in. This is going to be okay, so I am here. And now I am going to go to my notes. I am going to be posting these notes, but that's one of the things that I'm going to be doing. So I have to open the notes area. And then it's in one of these PowerPoint lectures. So I think I'm going to, and I have to guess because I'm, not sure about what day I'm doing this. So I'm opening this with PowerPoint, and I'm looking for it. Okay. Now what I'm doing is something that's, And maybe it's not in this day's lecture, maybe it's in a different day's lecture. So it's looking like it might be in a different day's lecture. See, that's one of the reasons that it's important that you look at the lectures and things like that. But I am trying to answer the student's question. Okay, so it's not that one. So we'll go back and we'll look for another one. Okay, and so the other one, someone's raising their hand, but are you trying to? Yes, it's Adnan. It looks like. Are you going to tell me which PowerPoint it is in?
I'm not sure. I can check the recordings later.
Well,
if
somebody
needed.
raised their hand. I thought they were trying to help, but anyway, you see, okay, so I'm doing this in Firefox. Okay, so I'm doing it in Firefox. Again, I'm going back to the notes. Okay. Now, Jesse Hayes Carver, over this weekend, he sort of volunteered that he might do this. I guess I'm going back all the way to this one. Okay, and I will see if it's here. So I'm opening this in PowerPoint. Okay, so I will enable editing and I will look in all of these and I will try to find it.
Professor Bradley, someone did say in the chat that it's in the second recording.
Yeah, but the recording, I'm not going to scroll through the recording. I have to look through here. And by the way, I do appreciate, and by the way, that's something that's useful for this student. And maybe this is the second recording. I'm hoping it is. Actually, I think this might be good. So hang on. And by the way, I do appreciate the student trying to help out and do that. So I'm trying to find it here. My guess it is in here. We'll find it if it is, and otherwise we'll look somewhere else. Actually, I'm becoming less interested in that. So I'm going to try to follow the advice, but I can't go through and scroll through a video recording. That's not what I'm going to do. But I am trying to find it for the student who, maybe wasn't able to attend that lecture. So what I'm doing is I am in Firefox now, so we don't get lost. And so apparently it wasn't there. But I will look in another one. Okay, so that was called Work in Progress, and this was called 613. This is called Day 2, and that was Work in Progress. Our second day was 614. I guess I didn't label it that way. And I think that's the one that I just looked at. So, so I'm opening this with PowerPoint, and maybe I will see if it might be in here somewhere. I guess maybe I could try to do a Control F, find, and I'm looking to find LSA, and see if I can find it in this PowerPoint slides. They couldn't find it. Okay, so here's what I'm going to do to answer that student's question. During the break today, instead of taking a break, I will go and find that so I can show the student who asked that what the LSA is, okay? And again, I'm going to go find it rather than, and I'm not going to invest everybody's time in, looking through the videos and things like that. Okay, so I will answer your question, but I probably would ask for you to stay tuned in because I'm coming back to answer your question, and maybe some other students have the same questions. Okay, so now I'm going back to that, and I will start my count again. So I will, answer that, but I'll be answering that after the break. So, it would be good if you can stay till after the break to get that question answered. So I'm going back to, this is 616, and I was all over the place kind of. And so Tony, I'm going to have to ask you if you can see the PowerPoint slide again.
Yep, I can see it.
Great. Okay. So we're doing questions. So that question had to be deferred because I didn't want to waste anyone else's time looking for that. So I will invest my time during the break to find that again. But anyway, I'm starting my count again in case there's other questions. Okay, I hit 10 Mississippi. Your questions are always welcome, including that question about the LSA, but it was taking me a while to find it, and when I was spending time finding it, I'm not just investing my time, I'm investing everybody else's in the class time. So I will invest my time during the break, and I'll come back with an answer for that. No one ask any other questions. Your questions are always welcome, of course. But we're going to close down this part of the questions. Now, I am doing our normal protocol, which means that around, let's see, we started at 11, so around 12:15, we will take a break. We'll take a 10-minute break, and then we come back for the second half, when I will be giving the answer to that student's question, and I will be and answering it for anybody else who needs that answer. We'll spend 50 minutes and we'll be adjourning, around 1:15 as we normally do. But today we're covering new material and we're covering arc length and surface area of revolution. So here we go. And that was the problem that I just did. Okay. And this, I don't know, I may have the wrong one open up here. Let me see. That should be the right one. So let me just, I need to find where we are in this slideshow because I was kind of going all around. Okay, so this is old lecture, and I'm going to go through and put the slides that I actually used. I am going to post them, but okay, so here we are. So this is the objective of what we're going to do. So we're going to study a new topic, and it's called arc length. And also, we're going to find a second topic that's called surface area of revolution. So the objectives here are, you are supposed to be able to find the arc length of a smooth curve. And so there's a formula and there's some integrals that you have to do. So you're memorizing the formula and you're applying it to solving a problem. And then we're going to find the thing called the area of a surface of revolution. So you see, both of these are going, this is going to be lengths. So this is, if I'm talking about units, this is going to be meters, but area happens in meters squared. So you see, we're moving from doing volume problems to doing length problems to doing area problems. So you see, there's a lot of different problems that we're solving. Okay, so here we go. So in this section, definite integrals are used to find the arc lengths of curves. And in fact, let's just talk about that. And later we're going to find the areas, surfaces of revolution. Okay. And so let's just talk about what does that mean. So you see this picture down here, you have a function that is called y equals f of x. And we're going from A to B. Okay. But you see, what we're talking about computing here is we're saying, all right, what we're going to do is we're going to say, how long is it? How many meters is it if you go from this point, A, and f of A, which is on the curve, to this point, which is B, f of B, but the path that you follow is along the curve. So this is what's the distance. It is in meters. So that's the problem that we're trying to solve. Now, in either case, and certainly in the arc length case, the arc, or the segment of the curve that I showed you, is approximated by straight line segments, whose lengths are given by the distance formula. Now, students should remember from the pre-calc that the distance between a point called x1, y1, and a point called x2, y2 is given by d, the distance. Between those is the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. So we have to think about that. And we are going to be talking about things that are called rectifiable curves. and that's one that has a finite arc length. And another thing about a rectifiable curve is that it is continuously differentiable on AB. Now, continuously differentiable means the first derivative has to be continuous. And we have a shorthand for saying all those words. We talk about a smooth curve. Now, the point is, in order to apply these formulas, f prime must be continuous. And sometimes that will help you figure out which arc length formula you're going to do. So there's not going to be a lot of focus on this, but you have to realize that we're saying, hey, if f prime is not continuous, that may influence what curve we use. So the distance formula. But let's go back and look at the picture then. So I told you what we're trying to do is we're trying to discern what is the length going from A, f of A to B, f of B, but we're following the path along the curve that's given by y equal f of x. Well, what we're going to do is we're going to slice this into pictures. And you say, oh yeah, this is kind of what we always do in calculus because calculus is the study of limits. So we pick a bunch of points, x0, x1, x2, all the way up to xn, and we slice it, and we're going to approximate the length of the curve by, we say, well, okay, we're going to say, hey, between, in this case, x1, y1, and x2, y2, which both are on the curve, what I'm going to say is, well, what happened if we just connected a straight line there? And so that straight line is the length of the straight line, and that actually will be given by the distance formula they talked about. So this little one is going to be the square root of y2 minus y1 whole squared plus x2 minus x1 whole squared, and it's the square root of all that. So the square root, but that's your distance formula. Now that distance is the hypotenuse of this little right triangle that I've drawn up here, because the x and y coordinates are perpendicular one with x and y axes are perpendicular one with another. So this little side here that I'm wiggling my cursor under is the change in x. So the length of this is going to be x2 minus x1, and we abbreviate that in calculus often as delta x. So this is delta x, and similarly, the difference between these is going to be y2 minus y1, and that is going to be called delta y. But I also told you this was a right triangle. So what that means is that this right triangle will be, the hypotenuse will be this. So you see for each of those, and you see we're drawing a whole bunch of those. For each of those, the lengths of those little line segments are going to be the distance formula. So in the ith representative one, it's going to be x sub I minus x sub I minus 1 whole squared. Plus, this is going to be y sub I minus y sub I plus 1 whole squared. And using different terminology of the delta x and delta y, this is going to be delta x sub I squared, and this is going to be delta y sub I squared. And I add up all of these things. And so now I have an approximation of the length when I add up all of those line segments. Now, it's not going to be much of a surprise to you that what we're going to do in a bit, though, is we're going to say, oh, let n go to infinity, and we're going to end up with an integral that is representing this. But for now, let's just say that s, and by the way, s is used for arc length in mathematics over and over and over again. So usually when you see an s, it will be talking about arc length. And we're going to be saying quite a bit about this as we go through. Okay, so far we have s is approximately equal to the summation as I goes from 1 to n of delta x sub I squared over delta y sub I squared. But now we're going to do a technique, and what we're going to do is we're going to, and the mathematical technique that we're doing is we're going to multiply and divide by the same thing. So we're going to be and that means basically we're not changing anything, we're doing 1. So you see what we're going to do here is we're going to take this expression and we're going to divide all the way through by delta x sub I squared. Now, when I divide this by delta x sub I squared, what I get is I get 1. So that's where this 1 comes from. And then I'm dividing this one by delta x sub I squared. So I get delta y sub I over delta x sub I squared. But that is all under the square root. And so what I have to do is, since I'm dividing by it, I have to multiply by it as well. So I'm getting a delta x sub I squared out here. Now, I am not going to make you derive this formula, but I am wanting you to understand how the formula works and why it works that way. So this is math tradecraft. So when I take then the square root, and by the way, in these notes, it's not, well, if we were in a room, I'd say this, but this square root bar should be over this thing as well. That is under the square root. So when I take the square root of delta x sub I whole squared, I get delta x sub I. And then I take the square root of this. So you see s is approximately equal to this. Now this has a different form than what I had up here because I did some mathematical manipulation of it. But now there's something that starts being very familiar. You see, when we let n go to infinity, this thing here, the delta x sub I, will become dx. And when that becomes dx, this thing in here, delta y sub I over delta x sub I, becomes y prime. Or if y is f of x, this becomes f prime of x. So we did this representative thing, we did the approximation, but now we're going to let n go to infinity. Now, what I talked about what happens when n goes to infinity, what happens is that this becomes s. And by the way, that was an approximation before. It becomes exact when we let n go to infinity. And so s, the limit as n going to infinity, that's this limit going n going to infinity, becomes, and this is the formula that you're going to want to remember because you're going to be using it over and over again, is that s is equal to the integral from a to b of the square root of 1 plus, this is f prime of x whole squared. And all of that is underneath the radical dx, where s is called the arc length. So this is the exact answer. So here's the definition. Now I am going to read this, and I think I'm going to, we're going to go through 2 examples of this, and then I'm going to pause for questions, okay? And the questions will go all the way back. So I'm making decisions about how we best use our time because I'm flying this plane. Okay, so here we go then. This is the definition of arc length, and I will read it for you. And by the way, as you're reading or as you're listening to this or studying it or making notes or something like that, it is important that you realize that, oh, arc length S can be defined in terms of dx, or it can be defined in terms of dy. And it depends on the problem which one you use. And I have asked problems on high stakes assessment where I ask you to do both of them. So anyway, sometimes it is dx and sometimes it is dy. I'm just giving you a warning about that. Okay, so let y equal f of x be a curve that we can do this. It is smooth, it is rectifiable. The arc length between AB is this. So if it is the dx formula, it is s is equal to the integral from a to b of the square root of 1 plus f prime of x whole squared dx. And by the way, you see if you're using a dx whole squared here. Similarly, if it is a smooth curve that is of this form, x equal g of y. Now we've done problems where, this is, so you're thinking about this. The arc length of g, if I'm going along the g of y curve between c and d, is s is equal to the integral from c to d of the square root of 1 plus g prime of x whole squared dy. Now this is the dy version, which means I have to have a derivative of something y here to integrate it. So those are the formulas, and I did show you where the formulas come from. I am not going to expect students to derive this from scratch, but I was trying to show you where it comes from. Now I have one more thing. Oops, that wasn't what I wanted to do. I have one more thing. I added this when I was talking to your sister class, and we'll come back to this again. Often in this course and in Calc 3 and in future things, when we will speak of something called ds. So sometimes we will talk about the arc length, just s, but other times we'll talk about something that is dx, that's the differential. So ds, so s is the arc length parameter, but what ds is going to be, ds, whenever we're using dx, is the square root of 1 plus f prime of x whole squared dx. This whole part here is ds. And when we're talking about dy version of this, this entire part is going to be dy. Okay, now we are going to go through 2 examples, and then I'm going to pause and ask for questions. Okay. Some students find these find these problems challenging, and I will tell you that one of the things that we debate in the math course is in what order do we do things, and I'm part of a collection of people who are trying to say, let's do it in this order. We might end up with some integrals that you can't evaluate yet, but we'll teach you how to evaluate them. And it really depends on how far we get with these examples. I have more examples probably than we need to do, but sometimes these problems aren't as easy as other problems. We'll see. Okay, so here's the first problem, and I almost skipped this problem with your sister class, but then when we went through it, we decided that it was kind of useful to talk about. Because it gets you familiar with the problem. So here, this is more of a theoretical problem, but it's kind of useful, so please follow along. Okay, so what this problem is saying is find the arc length from a point, and they're just calling this point x1, y1 to x2, y2, but we're going along the graph of y equals f of x equal mx plus b. Well, this thing down here that I'm waving my cursor on is a line, y equal mx plus b. So what is the derivative of this line? Well, the derivative of a line is its slope. So f prime of x is going to be m here. But if I'm going from x1, y1 to x2, y2, we know the slope by another formula too. It is m equals y2 minus y1 all divided by x2 minus x1. And by the way, y2 minus y1 over x2 minus x1 is a constant. Okay, so you see this is a very simple problem, but it allows us to get some traction on the way the formula works. So let's plow into it then. Okay, now I already said this part, but realize that yes, since we're on a line, f prime of x is equal to m, but m is y2 minus y1 over x2 minus x1. So these are just coordinates of some point here. Okay, so that means this is f prime. And everybody, please understand that this is a constant for x1, y1, and x2, y2 already picked. So what does the formula say? Well, the arc length formula said, well, okay, you're going to integrate from x1 to x2. And here we have, this is the formula for ds. And notice that I am using dx here. So this is going to be the square root of 1 plus x plus y prime, which is y2 minus y1 all over x2 minus x1. Okay, so I'm starting to plug things in. So f prime was y2 minus y1 over x2 minus x1. So I am plugging that in here where I have this squared version. Now, everybody please understand that all of this stuff that I am circling here with my cursor, that's a constant, because you see these points are given. So x2, y2, and x1, y1 are given. So this is a constant. Adding 1 to it's a constant. The square of that is a constant. So this is a constant that I'm putting my circle around. So you see, this is a constant. I could pull this out of the the square root. This is just a constant. So what's left to integrate? Well, I have to integrate. So pretend in your notes or as you're thinking about this, say, yeah, I jerked that through the integral, so that's just a constant out there. So what am I integrating? I'm integrating x1, x2, and I am integrating it from, and here I have 1 dx. Well, 1 is the same thing as x to the 0. So when I integrate x to the 0, I add 1 to the exponent, and I divide by the new exponent. So that's just x. So you see the constant is out here, but this is going to be a constant just times x. But now there is a little bit of algebra, and I'm going to talk about this, and it is important. Please pay attention, because this will come up over and over again as you're doing these problems. So I said the constant was 1 plus, this is is y2 minus y1 over x2 minus x1. But we're going to do some algebra on this thing under the radical. And this often will happen in doing problems here. That's why this is a useful problem to go through. So just look at this. So if you're adding 1 plus y2 minus y1 over x2 minus x1 whole squared, and I want to get a common denominator, the denominator over here with 1 is 1. The denominator over here is x2 minus x1 whole squared. So what I'm going to do when I get a common denominator is I'm going to multiply top and bottom here by x2 minus x1 whole squared. And so when I do that, 1 becomes x2 minus x1 whole squared divided by x2 minus x1 whole squared. So you see this part right here is 1. I got a common denominator. And then here I have the common denominator, but this is y2 minus y1 whole squared all over x2 minus x1 whole squared. So what I did here was just pre-calc. But now I also integrated it. So you see, I rewrote the constant this way. But now I have to evaluate x. So how do I evaluate this then? Well, I plug in x2 and I subtract off what I get when I plug in x1. So I have this. So this is the answer, but everybody look at this. x2 was bigger than x1. So the square root of x2 minus x1 whole squared is x2 minus x1 in the denominator. And this one is x2 minus x1 in the numerator. So those things whack with one another, they cancel out. And what is left with is the square root of x2 minus x1 squared plus y2 minus y1 squared. And that's kind of satisfying. So you say, oh yeah, if I was going along a line, I would expect this to happen. I have learned, and I learned this from your sister class, that it was worthwhile to go through this algebra. So this is a little bit satisfying. You might say, yeah, that was kind of a simple problem, and I really didn't need this, but you see, I get the answer I would expect. Okay, so that is good. Now I'm going to do one more example, and then I am going to pause for questions. Okay, so here is the next example that I'm doing. Now this is a more complicated example. We're finding the arc length of the graph of y equal x cubed over 6 plus 1 over 2x on the interval from 1/2 to 2. Now here's what's happening. This is a graph of y equal x cubed over 6 plus 1 over 2x. And we're going from 1/2. So this is when x is 1/2. and this is when x is 2. So we're finding, hey, when you go along this curve from this point to this point, how long is it? The answer will be in meters, okay? So that's what we're trying to do. Now, everybody look, I have a y here, and I am telling you that in this problem, I'm going to do the dx version. So you have to go back to the formula, but this is the picture of what we're trying to do. And again, I'm going to go and do the formula on the next slide, but you see, what do we need to do? Well, we're going to have dy dx. So we're going to take dy dx, then we're going to square it, and we're going to add 1 to that because that's the formula for arc length. In fact, I'm going back and showing you again the formula for arc length. So this is the formula that we're going to be using, the one that the one that I'm wiggling my cursor under. This is the formula we're going to be using for this one. Okay, so here's the problem that we're doing now is this one. So now what I'm going to do is I need to do that, but I need the derivative of this. So let's begin doing this. Okay, so now, in fact, I'm going back again. Okay, so when I take the derivative of this, that's a Calc 1 kind of problem, but the 1/6 just sits there, but the derivative of x cubed is, and by the way, you see, this is not an integral formula. I think this may be the first derivative we took in this class. And so this is going to be, the derivative of x cubed is going to be 3x squared. That's a different formula. You take the 3 times the x and you subtract 1. So there's n times x to the n minus 1. So that's going to be 3x squared. Now when I go to this one, this is going to be 1/2 times x to the minus 1. So when I take the derivative of x to the minus 1, it is going to be a negative x to the minus 2. Now you guys all know that, but that's what we're doing. So you see, when I do dy dx, the 1/6 just sits there, but this is what I said. I got a minus sign, that 1/2 is just sitting there. This is x squared. So this is what I get for my derivative. And algebra is your friend. And so it is convenient, and you learn this as you go through, but I'm going to simplify this to do the calculation that we have to do. And so my simplification is, this is a simple algebra thing. You see 3/6 is 1/2 and 1/2 is 1/2. So I can factor out the 1/2. And so this is 1/2 times x squared minus 1/x. So that is what dy dx is. Now, there's a little bit more tradecraft that's involved. You see, eventually, we're going to be squaring this x squared minus 1/x squared. And so there's some tradecraft, and I've learned that some students struggle with this. So I'm going to be showing you, and I apologize, this is I actually did this for your sister class. So we're going to say, well, what happens when you square this? Now, when you square this, look what happens. You're squaring x squared, so that is x to the 4th. But then we're going to have a middle term, which is going to be x squared times minus 1/x squared. So when I do x squared times minus 1/x squared, that becomes a minus 1 because the x squareds cancel out. And when I am squaring this, I get another factor of x squared times minus 1/x squared. So you see what happens is you get minus 1 and you get another minus 1. So this is going, and then I finally square this. This is minus 1/x squared, and I get 1/x to the 4th plus. But you see, I had two terms that were minus 2. So, you need to think about this, but this is something that a lot of students struggle with. And so that's why I showed you a little bit of tradecraft. And also, because this will come up in the problems repeatedly today, I'm going to say, hey, what happens if you had a plus there instead of a minus? Well, you still get the x to the 4th, but x squared times 1 over x squared is going to be 1. But I'm going to have another x squared times 1 over x squared as I'm going through. So I'm going to have 1 plus 1. I'm going to get a 2 there, plus, and then I'm going to take this times itself. I get 1 over x to the 4th. So we're actually going to see this happen. So these are things that will be happening before your very eyes. Okay, so that's the tradecraft that I'm hoping you remember. Okay, so now we're going to take this derivative and we're going to plug it into our formula. But our formula has the lower limit was 1/2, the upper limit was 2. And this is 1 plus dy dx whole squared. So this is 1, there's the 1, plus, and this is dy dx, but now I'm going to square this. Now, so look what you're squaring. Well, oh my goodness, I am squaring x squared minus 1 over x squared. And so that is going to give me the x squared, but x squared, I'm going to get a 2 in the middle, but the 2 is times 1/2. So that ends up being 1, and this is 1 over x to the 4th. So you see, when you multiply by the 1/2, after you do all that, you have a minus 1 that is there. Okay, but then what you're doing is you're adding a 1 to it. So what will happen, actually, when you square the 2, you're going to have a 1/4. So you see, what I'm going to do here is whenever I square this, I'm going to have a minus 1/2. You see it is 2 over 4. And then I'm going to add 1 to it. So I'm adding 1 to a minus 1/2. When you add 1 to a minus 1/2, you get a positive 1/2. So this is 2 over 4. And this is what's left. But this thing, this is the other part of the tradecraft, this thing here is exactly x squared plus 1 over x squared whole squared. So that means the square root is very easily handled. The square root of 1/4 is 1/2. The square root of what's left is, that was the square root of x squared plus 1 over x squared whole squared. So this is just x squared plus 1 over x squared. So you see, this ends up being a very simple integral to calculate. So let's do the integral. The 1/2 just sits here. I add 1 to the exponent. I divide by the new exponent. This is, so that is going to be x cubed over 3 minus, now this is x to the minus 2. So when I integrate that, that is going to be, add 1 to the exponent, that is x to the minus 1 divided by minus 1. So this is minus 1 over x. And the values here are 2 and 1. So I need to plug that in. I do expect you to be able to do calculations like this. So you have 1/2, and you got to get common denominators and things like that and simplify it. So the answer to this is 33 over 16. Okay, so that's good. So you see, what we've done now is we've done actually 2 problems. Both of them were DX versions, but we exercised this a little bit. But you realize, oh, there's some serious algebra here because you have to do some common denominators. And I refer to that, I mean, I could call it, oh, pre-calculus. But actually, since I'm not an evil teacher, I realize some students might not remember the pre-calc as well as they need to. So I make this note, and I say, note there is some math tradecraft here. And so what really happens is I've done 2 examples, and I think these are good examples. Now we're getting pretty close to the break, and I think I want to take the break on time. But there's going to be 2 things happen when we come back from the break. One thing is I'm going to go and find the LSA1 for the student who asked that question and any other students who needed to ask that question. So that's one thing we're going to do. But then I'm going to go back to this site. I guess I'm going to be busy during the break, but at least I'm just investing my time and not investing the whole class. But then I'm going to return to this. I'm going to do a count of 10 Mississippi in case students have questions on any of the things that we've done thus far. Can you still hear me, Tony?
Yes, I can.
Excellent, thank you. Tony, we're on break now, and we're going to reconvene at 12:25. Okay, so
Professor Bradley,
thank you.
we
Yes.
found the LSA problem, and we put a picture of it in the chat here, so I think you should be all right.
Okay, and maybe I'll just, okay, so, and thank you for that help, and that'll make things be pretty quick. I will check, I'm sure you did it, and thank you for doing that, that is very helpful. But I will go and I'll try to make something just so maybe it's not in the chat. So thank you for doing that, that is helpful. Okay, we are on break now. Can you talk? Okay, real quickly, and by the way, I'm not being rude and I'm not being mean, but it would take me a long time to write all this stuff, and I'm not going to do it. And by the way, I'm not trying to be mean. I'm just saying, okay. So there's two things. Administratively, you have to register for this course. Now, you can't do that until the dean's underlings do what they do, and they have to talk. So A has to talk to B, and B has to talk to C, and E has to do F, and all that kind of stuff. but she signed it, so it will happen. But you can't register because it doesn't exist yet. That's what that piece of paper caused to happen. So one day soon, I will say, it exists, register. And you will have to talk to a human being because they don't put it up on my access for you to register for. This is all just for you. So you will have to talk to a human being in registration to do that. Now you can talk over the phone and things like that, but you will have to, I'll say it a different way, you will have to in some way interact with a human being. So there is that administrative crap that has to happen, but you will need to do that. But I'm also going to say that you do not need to do that before we start doing work. And in fact, my advice is let's start doing work before that because time is wasting for us. So you and I, and I'm not, you see, I don't have things to even put anything where there for you. They will establish a Blackboard course just for you. There will be a Blackboard there, but it ain't there now, and that's after A, B, C, and all these people have to touch it. So that's going to take a while. Here's what I'd really like to do. Now, if you can't do it or can't do it until things, but I think the very best thing to do would be if you can swing meeting with me. And I know it's a physical meeting, but what I would do is I would hand you your practice exam and the key, and I talk about resources, and we would just have a face-to-face talk instead of, trading text and stuff like that. But that would be launching now. So, and of course I'm busy. I know you are busy, and so on and so forth. But I know I'm being aggressive and semi-rude with this. But can you meet me tomorrow? Can you meet me tomorrow? When can, I'm changing my question. And by the way, I'm not being mean. I'm on break. And so when can you meet me tomorrow? But this is a real meeting. What time can you meet me? Can you, I mean, I don't know if that means you, I mean, I don't know when you get up. I'm pretty much letting you pick a time is what I'm doing. All right, since you haven't picked a time, I will. I'm saying 10 o'clock. Now, this is not going to take us too very long to do, but I think it's important that we do it. Okay, so I'm going to say 10 o'clock. Now, the Learning Commons is not open, and I got to think about what that means for us. But I will plan to be at the Learning Commons. That's where you were, okay? Tomorrow morning and at 10 a.m. Okay, unless I hear from you, and I mean, if you say, "Oh, gee, something happened, I can't," I mean, that's all fine. But the plan is we will meet at 10 a.m. and we'll be done before 11. Okay, and so what, and by the way, I'm going to say this, the door will be locked, not the door to the college, but the door will be locked to that room. And so you want to go to the windows that are west of the main door where you walk through. And gee, I lost my whole break here. Okay, anyway, so you will go to those and you will knock on them. And I should be working in, I'll be working there and I should hear you knock. And by the way, if I'm not there right now, I'm taking a piss or something, but I'll be back very soon, okay? And I'll try to plan my piss so I'm not doing it at 10 a.m. Okay? Okay, see you then. Bye. Uh, Tony, are we back?
Yep, we're here.
Great. Okay. And by the way, I apologize. I actually was on a phone call and I was talking to a student, but it's a student I know very well. And I used some salty language and I didn't realize that I was online. And so I apologize for using salty language. I actually have a pretty decent vocabulary and I don't have to use that language, but I sometimes do. And by the way, I wasn't yelling at the student, and they in fact were kind of laughing when I used the profanity. So I apologize for that. Okay, so let's. All right, so now and Tony, I'm going to ask you. You're seeing a chart that says LSA, yes?
No, we can't see anything.
Okay, so I need to fix that. Okay, so I need to go back to Blackboard. Ah, God, so here is Blackboard. And wait, you guys are 04. That's the wrong Blackboard. I may have to go in and log into Blackboard again because of doing this. I guess that's okay. All right, so I'm logging into Blackboard again because I have to do that because I have two sections. You guys are 04, so just bear with me. I will be there in a bit with you. Okay, so I go to my institution. I'm looking for 04, so I'm clicking on that. And now I'm trying to go to Collaborate Ultra in the class called 04. And so I'm going to the thing, I'm joining the course room. And my browser isn't supported, so I go there. Uh-oh, you've already joined the session. All right, so I need to try to think through how to do this because I was going from a different browser to do that. And so I need to go back here and I'm going to try to go here. Now this is 04. So I am supposed to be in here in 04. So I'm here. I am in the classroom. It says get secure length. So I'm not sure what all this means. I am in the course room. Maybe I'll try to go to settings and see if I can go anything with that. No, that's not what I want to do. Yeah, that answering that question was a complicated thing. Okay, okay, I'm going to try to go into the course room again. And I'm here, now I'm joining the course room. And it says I'm joining this again because I've already joined the session. So you see, I have to figure out how to maneuver around this. I think what I'm going to do is I'm going to have to okay, so I'm going to have to, all right, so I'm logging out completely. I'm going to be logging Okay, Tony, can you see can you hear me first of all, and can you also see a PowerPoint slide?
Yep, I can hear you and I can see the PowerPoint slide.
Thank you. Okay, so Dylan or whoever asked this question, here is the LSA, and thanks to the students who went and got this. I was going to get it, but I ended up talking to another student about another issue, so it was good that this was done. So Dylan, this is the slide that was in the lecture for you, and so I'm going to say that this is LSA 1. It is due before midnight on June 19th. And so what it says is, I realize I'm reading it to you, but it says consider y equals f of x. This is the absolute value of 2/3 x cubed minus x squared minus 11 over 3 times x plus 2. And I ask you to do two things. I ask you to graph this function. So you should graph this function. And then I ask you to find the area of the region between this curve, the line x equals 0 and x equal 4. Now, I realize that you can do Chegg, and you can do all kinds of technology and stuff like that to do this. A sincere student would realize, oh, Jim expects us to be able to do this, so you really should do it using the tools and things that we that you will have access to on a high stakes assessment. And Jesse Hayes Carver has created places for you to turn this in. And so anyway, that's what we have. So and by the way, I guess I will say, whatever student asked this question that started this, are you good with this now?
Yeah, I got it. Thank you.
Okay, and you're the student who asked?
Yeah.
Okay, good. So the question is asked. And by the way, all questions are welcome. Okay. So and one of the things that either I or Jesse Hayes Carver will be doing is maybe throwing this up somewhere. And actually, I didn't plan. I know I'm talking, but I didn't plan on doing this LSA. But there was a student that asked, well, I don't understand about LSAs, and I say, well, the best way for me to do it is to give you one to do. So here is one to do, and so you will have an LSA grade for this. Okay, so now I need to search through and find out where we were, and I'm going to count to 10,
Professor Bradley?
Mississippi, in case there's questions. Yes?
Sorry, I thought at the beginning of the course that you said the LSAs were due on Fridays. I just wanted to, like, is this normal that this LSA is due the Sunday, or are they still sticking to like Fridays at midnight?
Now, by the way, please understand I'm not being rude with this, okay? When, and I'm really asking you, when do you want this to be due?
Oh, I'm happy with the Sunday for this at least.
Would you rather it be Friday? Well, I guess Friday, I need to look at a calendar. I could make it due Friday, I suppose. I'm trying to look at a calendar here. Oh, shit. Okay, I need to find the calendar now. Okay, so tomorrow is the 17th, so Friday is the 24th. Okay, so I'm changing this to June 24th, and I'll try to tell. Oh God, let's see, how can I do this? Hold on. I actually know how to do all this stuff. It's just very awkward doing it. Okay, so, and I'll tell Jesse Hayes Carver about all this. I would like to have these due so that people were encouraged to go to GSGs. Okay, so it's before midnight on June. I guess I said that is 24. Okay, so I will. I'm saving this, and eventually this will get posted, and things like that. Okay, so I've answered your question then, yes? And I'll
Yes,
tell
thank you.
Jesse that the students like to have this due on Fridays. Okay, so we'll do that. Okay, and so that's good. Now we're going. So that question is answered. And we're going back to math. Okay. Okay, so we did two examples, okay? And we got to this point here. That was the first example we did. And we just did the second example that was there. And so Tony, I think this is where it is. So I'm beginning to count right now. And so I'm beginning to count for students to ask questions. I'm going to count to 10, and if students ask questions, I'll restart the count. Okay, so it's any questions, sort of arc length up to the end of this slide that students may want to ask. Okay, I hit 10 Mississippi and there were no questions. Now your questions always are welcome, and so please understand that. And but we will go on and we'll do probably another problem. Now this was the tradecraft. Here's the new problem we're going to do. The next example. So it is called finding arc length. And so the question says, find the arc length of the graph of y minus 1 whole cubed equals x squared on the interval 0 to 8. So you see, this is the graph of y minus 1 whole cubed equal x squared from x being going from 0 to 8. So what we're finding out is what is the length. And so the length of this would be like meters. So it's the length going up, but the path we're going along is along this curve. So that is meters. So that's the problem we're trying to do. Now, if you're looking at this, you're probably saying, well, wow, it's not clear to me what is the best thing to do with this. Is it best to do this dx, or is it best to do this dy? And the real way that you'll learn that, well, sometimes I will give you questions where I might ask you to do it both ways, and often you can do it both ways, but you don't know yet. You have to kind of wade into it. And so we're just going to wade into it now and see what happens. But one thing we know for sure, we know the formula is going to be the square root of 1 plus a derivative whole squared, and then it's either dx or dy, and we need to integrate this. And so if we're doing this dx, we're going to go from 0 to 8. If we're doing it dy, we're going to go from 1 to 5. Okay, so let's dive in and do this problem. Okay. Now, so this is the investigation that you might do. So solving for y, and so we're solving this equation right here for y. So that means we're going to take the cube root of both sides. Now, when we take the cube root of both sides, this is going to be x raised to the 2/3 power. So the first algebra step would be y minus 1 is equal to x to the 2/3. But then we're just going to add 1 to both sides. So we'll find out that y is equal to x to the 2/3 plus 1. And we're just going to try to see, will that work? Okay, so solving for y, as I said, yields x to the 2/3 plus 1. But now we know then that if we're going to do this problem dx, then we need to have the derivative here, okay? And by the way, the derivative has to make sense then, because x goes from 0 to 8. So we're looking at this and we're going to say, okay, so we have dy dx. We need to take the derivative of this. Now the derivative, and you see, you do have to know Calc 1 taking derivatives. So the derivative of 1 is going to be the 0. The derivative of x to the 2/3 is going to be 2/3 times 2/3 times x to the 2/3 minus 1, or x to the 1 minus 1/3, but that's in the denominator. So dy dx then is going to be 2/3, and this is x to the minus 1/3. Now the reason it's written this way is because you have a parentheses, and that's in the denominator. But if you look at that, you say, oh damn, that's not defined when x is equal to 0. So an alarm goes off, And that tells you I can't do the problem this way because the first derivative is infinite at one of the points that I have. So we can't use the arc length formula with respect to x. We can't do this dx. Okay, so we just say, well, okay, we'll have to do it dy. Now, if you're doing this dy, that means we have to solve x in terms of y. And we're going to be talking about dx, dy. But let's talk about solving that. So what we would do is we're solving for x, we would take the square root of both sides. Now, when you take the square root of both sides, you would find that x is equal to, and by the way, when you take the square root, you might say, oh, it is plus or minus. But look over here, on the graph that we're studying, is x positive or negative? It is only positive, yes? So we're going to take the positive square root. So this is x is going to be the positive square root of y minus 1 whole cubed. But the square root of y minus 1 cubed is y minus 1 to the 3/2. So that's what we're going to solve for. And so we say, oh, I can't do dx, but I'm going to do dy. So solving for x in terms of y, and this is the plus and minus business that we can just throw away. So we conclude that x is equal to, and it's the positive because of the reasons that I said. This is y minus 1 whole to the 3/2 power. And I talked about why we chose positive because we knew what the picture looks like. But now we have to take the derivative of this. So what this is going to be is it's going to be 3/2 y minus 1 whole to the, I subtract 1 from this. This is 3/2 minus 1 is 1/2. So dx dy is 3/2 y minus 1 whole to the 1/2. So you see, we need this. And we know now that because we're doing it this way, we're doing dy, not dx. So that's why there's a dy there. And that's why when we think back about the problem, these y values are important. Now, we started with x being on 0 to 8, but I figure out the y things just by plugging into the problem. So if I let x be 0, so I'm putting 0 here, y has to be 1. If I let x be 8, I get 64. So we get that that is 5. I mean, you just plug it in and you get those values. Okay, so we have the derivative, we have the limits. We're going from 1 to 5, and we know our formula. It's going to be the square root of 1 plus, this is dx dy whole squared times dy. Now, this is a little bit of, I don't know, tradecraft hint, but if you're using dy, you better have a dy down here in order for that formula to make sense. But we found that dx dy was this thing, but we're going to square it. Now, everybody realize that when you square y minus 1 to the 1/2 power, you just get y minus 1. So you see, this ends up being kind of it will be a very doable integral. But I'm also squaring 3/2. And when you square 3/2, you get 9/4. Okay, so I'm just plugging in here, and this is just a kind of an obvious plugging in here. And so I'm integrating from 1 to 5. This is a dy problem. This is the square root of 1 plus, and then I'm plugging in what dx dy is here, and I know I have to square it. Okay, now this is some algebra tradecraft that kind of has to happen. So, and I'm not going back to the whiteboard on this, but I'm just going to say you do want to work through this because you will have to work through things like that in order to deal with a problem like this. Okay, so when I square 3/2, I get 9/4. And so this is going to be 9/4 times parentheses y minus 1 close parentheses. So I'm taking 9 over 4 times y. There is 9 over 4 times y right there. But then I'm also taking minus 3 halves. Or no, I'm wrong. I'm squaring that. So I'm also taking 9 over 4 times. This is minus 1 after I square it. So this is minus 9 over 4. So you see, I get this minus 9 over 4. But I'm adding 1 to minus 9 over 4, and that gives me 9 over 4 y minus 5 over 4 dy. So there's algebra involved here, and that's tradecraft, but I think, we kind of done that. And you should practice this algebra because it will be difficult to do these problems if you're not doing the algebra. Now, and then this is techniques of integration. Now you can do this all kinds of ways, but I'm just telling you how I'm looking at this problem, and I'm a practicing mathematician. I'm your teacher and everything else. I will 10 times out of 10 pull out a common factor if there is a numerical factor. So when I look at this, I say, oh, there is a common factor, which is the square root of 1/4. And the square root of 1/4 is 1/2. So I would jerk the 1/2 out of this integral, and I would have this left. Now this really isn't too bad of an integral, but it does build upon your Calc 1 skills. So you got to do a U substitution on this, and your answer will be a number. And as long as you do the integral right, you will get the right answer. So here is going to happen a U substitution, and you're going to get U equal 9y minus 5. So du is going to be 9u du, and when I substitute back in for the dy, there's a factor of 1 over 9 that comes from the substitution. So I get a 1 over 9, and that's where this 1 over 18 comes from. Now this then is what I called u, and so this is u to the 1/2. So I add 1 to the exponent on u, so it's u to the 1/2 plus 1 is u to the 3/2 divided by the new exponent, which is 2/3. And when you divide by 3/2, that's the same thing as multiplying it by 2/3. So this is 2 over 54, which reduces to 1 over 27. And then you have to plug these numbers in. Now, and when you plug them in, though, you see I took all my numbers out here, so I'm really just plugging the 5 and 1 into this expression. So a exact answer to this problem is 1 over 27 times the whole of 40 to the 3/2 minus 4 to the 3/2. There is no more calculation done. That is, in fact, the exact answer. And if I ask you this question on or a question like this on a high stakes assessment, I would expect you to give me an answer that is exact, and you have it there. And you want to do some simplification. I don't want you to give me a string of fractions and say I don't know how to use fractions, or and actually I once upon a time actually I was teaching Calc 2 with this student, and this student came to my office hours, and the student said, I'm a concept guy. I'm like Steve Jobs for Apple. That's who I am, and I will have peasants who will work for me who will add fractions together. So no, I refuse to add fractions together. He had a bunch of issues, but I expect people to add fractions together. And again, I'm not trying to be unreasonable. It's just, you see, either he adds the fractions together or I add the fractions together. And I used to have a whole, I sometimes talk about this, I used to have a whole bunch of very high-priced engineers who reported to me, things like that, and they were very good people. But I expected them to add the fractions or give me an answer. They didn't turn in work and say, oh yeah, and here, why don't you finish this problem? And again, I know you guys are hoping, in fact, it would be a great thing if you guys end up being as well paid and as well engaged as those engineers are. So, adding fractions, yeah, so, do your best to simplify the answer. And again, I'm not trying to be an SOB here or anything like that. I'm just saying I've worked in industry. I know what's required of engineers. I expect you guys to learn calculus. And also I have to, teach calculus the way the math department wants to do, and so on and so forth. So anyway, I do expect you to give me exact answers, except on perhaps some LSAs where, I'm saying, hey, you can use calculators here. But this is an exact answer. Okay, now I'm going to pause for a count of 10 Mississippi in case there's questions on this example. And I do have other examples, but we've done one that is dx and one that is dy, and I do keep my eye on the clock. And so, we have other things that we're going to cover as well, but I want to entertain your questions here. So if your questions, I'm starting my count right now, and Tony, you guys are still out there, right?
We're still here.
Great, thank you. And Tony, I know what you're probably saying. What is this? This is really some of the students might say, this isn't so good from our end. It's not so good from this end either. It's kind of a mess. But anyway, I'm starting my count now, and I'm soliciting your questions. I at 10 Mississippi. So, I mean, there's the most, and I am kind of an optimistic guy. So I'm going to say, okay, you maybe did a good job of explaining this one, and there are no questions. I suppose it could be people are lost or they don't know about questions, and that, I really do want you to ask questions, you have them. But we're just going to go ahead then. Again, your questions are always welcome, though. So please understand that. Okay, so we'll continue going, and I'm trying to think of how I want to do this. Okay, I'm choosing to do at least one more of these problems. Okay, so we're doing this problem, and we want to find the arc length of the graph, the arc length from 0 to pi over 4. Now, on this picture, here we're going from 0 to pi over 4 of the function y equal the natural logarithm of the cosine of x. So, we're finding the length. You're going from this point to that point. And how long is that in? I'm just going to say meters because that is a length. Okay, so there we go. And we know the arc length formula. That's one of the things that you commit to memory so you can use. And we know that and by the way, just looking at this, we're going x going from 0 to pi over 4. So I said, well, I know about 0 to pi over 4, so I'm going to investigate first to see if I can do this dy dx. Now, by the way, if I'm doing this dy dx, though, that's the same thing as saying I'm integrating here with dx. And it turns out that works, but as you saw last time, sometimes it doesn't work. It's up to you to think about that. But I need to find what is dy dx. So dy dx then is going to be, now this is a composition of functions, so I have to use the chain rule. So this is going to be, and the derivative of the natural logarithm of u is 1 over u times du dx. That is the chain rule. So the derivative of this with respect to x is going to be 1 over cosine x times the derivative of cosine x. And the derivative of cosine x from your Calculus 1 class is minus sine of x. Okay, so that's the calculation that is illustrated here. So dy dx is equal to minus, here's the 1 over cosine x, and there's the minus sine x. And it's kind of tradecraft, seeing where the problem is going, but it's going to be very useful for us to have a more simple expression for this. And the more simple expression that we have for this is going to be the sine x over the cosine x is equal to the tangent x. So negative, this quotient is negative tangent of x. So this is a nice way to plug in. Now here we already realized that we're going to use, or you see it's making sense for it. In fact, let me just go back and show you there's no problem here. There is no problem using this, this function because the derivative, the tangent, in the first quadrant, the tangent is 0, the tangent of this is 1. That's we don't have any problem with this derivative. The derivative is finite all the time. So anyway, we're integrating from 0 to pi over 4, and I'm just plugging this in. Now, when you square the negative tangent of x, you get tangent squared of x. So this is the square root of 1 plus tangent squared of x dx. So that's what we've got going on. Now, often in calculus, and we did some of this in calculus 1, and you're going to be doing a lot of this in calculus 2. Often you have to do a trig identity in order to compute an integral, and you have to remember the integral formulas and things like that. And so what this is this is a trig identity. So 1 plus the tangent squared of x is equal to the secant squared of x. Now you see so this was a useful simplification. This is another useful simplification because now we're talking about the square root of the secant squared of x. Now, the square root of x squared isn't always x. The principal square root of x squared is the absolute value of x. But a nice thing about the construction of this problem is that 0 to pi over 4 is in the first quadrant. That means all trig functions are positive. All trig functions are positive in that interval. And so you see, even if I wrote down this as the absolute value of secant of x, that really is just the secant of x because the secant of x is positive here. And now we have to remember the antiderivative of the secant of x. And the antiderivative of the secant of x is from your Calc 1. And by the way, when I'm going to hide that just so you're that was in your way. So the antiderivative of the secant of x, and I am going to tell you that I've taught this course many times, and that actually comes up quite a bit in this class. So what you want to do is remember it. And I also will tell you when I teach Calc 1, and we come to that formula, that's about a half of a lecture explaining why this formula is true. But I do that in Calc 1. My advice to you in Calc 2 is just know the formula. But the antiderivative of the secant of x is the natural logarithm of the absolute value of the secant of x plus the tangent of x. Now, we're in pretty good shape here. You might say, oh, the absolute value is complicating things. Well, not so much because, as I said, you're in the first quadrant, and so all trig functions are going to be positive. So we're going to be plugging in pi over 4 and 0. Now, and again, this is a very non-calculator friendly problem because pi over 4, the right triangle associated with pi over 4 is a 45, 45, 90 triangle. And so a 30, 60, 90 right triangle and a 45, 45, 90 triangles are things that you know what they are. For example, the secant is the reciprocal of the cosine, and the cosine of pi over 4 is 1 over root 2. So the secant of x is going to be root 2 because it's the reciprocal of the cosine. And the tangent of pi over 4 is going to be 1. So you see I get, when I put in the pi over 4, I get root 2 plus 1. Now, when I go to 0, what's going to happen is I plug in 0. Again, this is a reciprocal. So the cosine of 0 is 1, so the reciprocal is 1. The tangent of 0 is 0. And so what you get is the natural logarithm of 1 here. Now, it turns out the natural logarithm of 1 is 0. And so this is just going to be 0. So the final answer to this question is it is the square root of, it's the logarithm. And the argument of the logarithm is the square root of 2 plus 1. And so that's the final exact answer. And here I show, well, gee, if you were doing an engineering, plug that in a calculator, you could get an answer like that. But we're not using calculators here for all kinds of reasons, including it's a math department rule. So the answer is the natural logarithm of the square root of 2 plus 1. Okay, so I'm going to pause here again for a count of, let's see, what do I want to do? I'm going to count to 10 and see if people have questions on this. Okay, I hit 10 Mississippi. Again, your questions are always welcome, but we have this. Now, let's see, is this my last example? It is. Okay, so I'm going to talk briefly about this example. Now, this is a very applied example, and I did work at Bell Labs and in the telecommunication industry, and we actually were concerned about this, and this is something you study in your physics. So here we go. This is a very applied problem. An electric cable is hung between two towers that are 200 feet apart. So you see you got these towers are 200 feet apart. And I might not draw this picture for you, but they have a picture here. I just left it there. But the cable takes the shape of a catenary. And by the way, when I teach differential equations, I actually show that it does take this shape of a catenary. And the catenary, it is defined in terms of a hyperbolic cosine. And that is, and this is like if you say a hot dog is kosher, this is pronounced kosh, just like that. And this comes up in applied math all the time, and we will study that later. But we get this. But just using the definition of the kosh, and I'm not trying to explain that to you. This is just here. So this is 75 times, and it is e to the x over 150 plus e to the minus x over 150. And 75 times all that. So that is what y is. Now, what you have to do, and the question is, find the arc length, find out how much cable do you need to interconnect these towers. So it's find the arc length of the cable. Now, you do have to introduce, and by the way, the problem doesn't always come with a blueprint, but you understand the problem, and you can overlay, as an engineer, a coordinate system on this. And so I'm saying, okay, and how do you know what to do? The way you know what to do is through experience. So I'm just showing you something that'll work, but you can pick 0 over 0, 0 here. Now you can pick different coordinate systems and everything else, but this is a very convenient one. And so if this is 0 over 0, this is going to have a y-intercept. We get this from the graph of 150, and those are going to be at minus and 100. But now we can now we have an equation for y, so we can take the derivative of this. Now when we take the derivative of this, you do have to use the chain rule. So the derivative of this is going to be e to the x over 150 times 1 over 150. And this is going to be, the derivative of this is going to be e to the minus x over 150 times minus 1 over 150. Okay, so we're kind of do that, but we're going to do that. So we take the derivative, and this is the simplification of, so this is y prime. Now notice that the minus happened here, and but then we're going to square it, and we're going to be squaring this. Now, I want everybody to understand that I'm trying to think of how I want to say this. If I took this number times this number, e to the x over 150 times e to the minus x over 150 is 1. That's like the tradecraft that we talked about before. So you see, when you square y prime, you get this minus 2 here. That's the tradecraft, the algebra that we talked about before. Now, please note that this is y prime, but what I have here is a minus 2 divided by 4, so that is a minus 1/2. So if I add 1 to a minus 1/2, I get a plus 1/2. Here's 2 over 4. Now that makes this really kind of convenient. And the other part of the tradecraft is, we talked about what happens here. If we say, well, what is this? This is actually going to be, if I square 1/2, I have a 4th. And this is what I get when I square this with a plus instead of a minus. This is actually exactly the tradecraft that I had talked about before. So you see 1 plus y prime squared is going to be equal to, this is 1/2 squared, and this is this business squared. But you see the formula is just taking the square root of that, so I'm plugging it in. And so this business, when I take the square root, it's just going to be, there's the 1/2, and there's the square root. So you see, this is a pretty easy integral to evaluate. Now you do have to do a change of variable here and things like that, but the integral of e to the u is going to be e to the u except for a constant, and the integral over here is going to be e to the u except for a constant. When you change the variable, this becomes a minus, and so you do want to check that. You plug in these things, and this simplifies to 150 times, and this is e raised to the 2/3 minus e to the minus 2/3. You don't need a calculator. I know what those are, and I certainly would accept that that answer. So that's what we had for that. Okay, so I'm going to pause for a count of, and by the way, some students, and by the way, I talked about, I love the people that worked for me in industry, and I love my students, so I love all you guys. But I'm going to tell you that sometimes when we hit this lecture, students sort of say, oh my goodness, I've really got to be brushing up my pre-calc skills and my trig skills or my calc 1 skills. And that's not unusual, okay? And it doesn't mean you're doomed to failure. But if you find yourself on this date feeling that way, you kind of say, okay, I got my work cut out for me. Now, fortunately, we have a whole bunch of things. I'm a good pilot, and if you come to my office hours, I will help you and in things like that. I also have a first-rate co-pilot in Jesse Hayes Carver, and he can help you with that. And so not only do we have this flight crew who are very experienced in these matters, but we also have a very significant ground support, the Learning Commons, and they have over 70 hours a week of being open. They have virtual resources, they have face-to-face resources. I gave you a one-click access to them. And so you can do this, okay? But this is what's in front of you. And again, I love you and I want you all to be successful. So trust your flight crew and trust the ground support, but keep your seatbelts fastened and fastened. And some of you may be facing digging in. Now, another thing, in addition to saying, oh, gee, it's wonderful that you have some really, you have a good flight crew. It's wonderful that we have a Learning Commons. By the way, the people that work in the Learning Commons in the math assistance area are instructor quality people. And Jesse Hayes Carver is an instructor, is an instructor quality person. And so, there's a lot of help available. And so you can, you can dive in and do that. And I want people to be successful. But like I said, there's a wholesome discipline that's involved here in having somebody go into Calc 3 and other subsequent courses without having the Calc 2 there. And again, I told you my number one thing is teaching you the best Calc 2 course I can teach you, and that is my number one objective. Okay, I'm going to pause for a count of 10 Mississippi on this problem in case there's questions. Okay, again, I don't always know what that means. I am keeping track of the time, and we have 4 minutes left, and I don't want to waste time. So what we're going to do is we're going to go into the next section. Now we're going to start the next section. Now, one of the things that I am very keen on doing is keeping the two courses together as much as possible. And so what's going to happen is I'm going to start this next section, but I'm not going to finish it in the classroom right here. But what I am going to do is, and you see, I do, oh, and I know I said this earlier, but I want to say it again. At the College of DuPage during the summer, we have long weekends. And so what happens is there's a Friday, Saturday, and Sunday. Now, I tell you what I do on my Friday, Saturday, and Sunday is I do math. And students can do that also if they have catching up to do. That that's a good time to do some of that kind of thing. I will be doing some catching up as well, and I will be making a video that I'm going to encourage you guys to watch. It'll be a YouTube kind of thing, and it will finish. It will get you VCM04. It will get you back. I mean, you will have heard the lecture that will get you synchronized with VCM02. And so, I'll do that, and I'll send you an announcement about where that is and everything else. Now, I am starting that right now, but I'm also sensitive to the time. So we're not really, going to finish this, but I am going to start, and maybe this is the first thing, but this next thing is we are going to be computing an area now. And before, when we were talking about volumes, those were cubic meters. And when we're doing arc length, those were meters. Area is back meters squared. And so we're saying we want to find the area of a surface of revolution. Now, the way I often speak about that, I'm wiggling my fingers over here, is a good way to think about this, I think, is if you were painting the outside of a solid, you're not painting the inside of the solid, you're only painting the outside, how much paint would you have to use? In fact, you're saying, what's the surface area of the surface? So I'm going ahead and showing you a picture here, and I'll talk about this in the video. But you see, what we're really saying is, okay, suppose you had this thing that looked like this, and you were just painting the outside of it. How much surface area do you have? That would be square meters. That helps you know how much paint you need. Okay, so that brings us to the end. It is important that young people be safe this weekend, so please be safe. It is a long weekend. I hope you enjoy the weekend, and for some of you, it's going to be useful for you to be doing some math, I am sure. So I am going back to, I don't know if I canceled that thing or not. And by the way, Tony, thank you so much. But I am canceling, or not